Hello and welcome. This is Bhaskar Napte from Pharma Growth Hub, and today we are going to talk about why you must add water in the mobile phase of normal phase liquid chromatography. So mostly the non-polar liquid chromatography has the hydrophobic or non-polar mobile phase and the polar stationary phases or the columns. And we all know that the water is one of the highly polar solvent. So what is the benefit of adding this highly polar solvent in the normal phase liquid chromatography? What actually gets changed once you add the water in the normal phase liquid chromatography mobile phase is going to be the point of discussion today. So as we know that the mobile phase used in the normal phase mode is always non-aqueous. They don't contain water. They may contain less non-polar solvents like alcohol, but preferably they do not contain the water. So what is going to be the retention mechanism in case of such non-aqueous mobile phase system? And it is going to be more or less adsorption. So based on to the adsorption, the retention of your compound is going to get governed. So which compounds are going to get adsorbed onto the stationary phase? So there will be a competition between the sample and the mobile phase for polar adsorption centers localized on the specific site on the adsorption surface. Let us take an example of this bare silica column, and the silanol groups are the polar adsorption centers. So in case if a mobile phase also contain the polar solvent, maybe like alcohol, and now your analyte is also polar in the nature, and hence these polar moieties are going to get compete between each other for these adsorption sites, means the silanol groups. From mixed mobile phases, means the mobile phases containing, let us say, the polar organic solvent and the non-polar organic solvent. You can imagine the mixture of maybe methanol and maybe n-hexane. So which one is polar in case of methanol versus n-hexane? So methanol becomes more polar. So these polar solvents are preferentially adsorbed on the surface of the polar adsorbents. Now why? The methanol, which is a polar solvent, gets preferentially absorbed onto the stationary phase because our stationary phase is also polar in the nature, like silica having hydroxyl group. Now this is the rule which is very important to understand, like attracts like rule. So the polar solvents like methanol can get easily preferentially adsorbed onto the polar stationary phase containing like silica or silanol groups. But sometimes what happens, these polar solvents are also miscible in the water. Like methanol may contain a little amount of water, ethanol may contain a little amount of water, and this little amount of water, which is trace level of water, may get absorbed onto these highly polar adsorption centers. So, as we know that the water is the highly polar solvent. Now, who is going to get these polar centers present onto the column? I'm talking about the silanol groups. So these silanol groups preferentially can form the hydrogen bond with a highly polar solvent like water rather than making this hydrogen bond with the less polar solvent like methanol or maybe ether. So because of this trace level water present into this solvent, the water molecule is actually going to form a thin sheet onto these active sites of the stationary phase. In another word, the waters which are present into the organic solvent which you use for making the mobile phase can actually block this silica adsorbent site. They form the thick layer of absorbed water, rich liquid stationary phase and because of that, you are going to limit the interaction of your analyte, especially in case if you have the protonated base like BH plus. Now these silanols are not available to interact with this protonated base. Now why they are not available to interact with the protonated base? Because these silanols have already formed the hydrogen bond with the water. And where the water comes? The water comes from the organic solvent or the water miscible organic solvent. So increasing the content of adsorbed water gradually deactivates the adsorbent and dramatically decreases the sample retention time, affecting the reproducibility. So more is the amount of water content, more will be the deactivated adsorbent site, and the less will be the retention time possible. In case of less amount of water content, the amount of deactivation will be less and the retention time can be slightly higher. But in this process, as you do not have the amount of water present inside your mobile phase, you always struggle to achieve the reproducible retention time. Your day-to-day operations may have the different amount of water present into your mobile phase, and because of that you will end up getting the different retention time. So achieving the retention time consistently becomes the number one challenge in case if you use the water miscible organic mobile phases in the NPLC mode. So more water means less retention, and the higher water means the more water means less retention, and the less water means the more retention. What is the solution now you can think of? The first one is what you can think of: removing the water from the non-aqueous mobile phase. I mean, by using the solvents which are completely dehydrated. So there is no question of water in the mobile phase, and hence there will not be this water and silica interaction. So whatever silica or the silanol groups are present inside the stationary phase, they will be available to interact with your protonated compound or the analyte. And that way you can expect the consistent retention time. Now, what is another way to improve the reproducibility? By deliberately adding the small amount of water in the mobile phase, such as 1%. Now, provided your mobile phase component should be miscible with the water. Mostly alcoholic mobile phases will not have any issues with the water miscibility. But once you add this little amount of water, right, like maybe 1% or 2%, now there is a fixed amount of water present, and because of that there will be fixed amount of deactivation of these silanol groups. So I think you may end up in a little less retention time, but now your retention time is going to be more consistent and reliable. Now in case if you have the bonded stationary phase like amino or cyano, again, this bonded stationary phase will also have the leftover free silanol groups. And these free silanol groups can certainly interact with the highly polar solvents like water. The small amount of water inside the mobile phase is going to occupy these free silanol groups. So if you deliberately add a small amount of water, maybe 0.5% or 1% in your mobile phase, this water is going to occupy these free silanol groups. Now, because these free silanol groups gets occupied with the water, they will not be available for the interaction with your analyte. And because of that, now your secondary interaction gets completely eliminated. And what is the benefit of elimination of the secondary interaction? Better peak symmetry and increased plate count or the efficiency. So what is the conclusion all over by addition of water in the normal phase liquid chromatography mobile phase? The first one is If the mobile phase contains alcohol or other relatively polar miscible water solvents, the random variation in the trace amounts of water in such a polar solvents tend to make the method irreproducible on day-to-day, analyst-to-analyst, and lab-to-lab basis. The trace amount of water present in the mobile phase could interact with the free solenols, and these sites would not be readily available to the analytes for the interaction. In this way, the secondary interactions between analytes and the stationary phase could be minimized or even completely suppressed, which would result in improved tailing as well as improved column efficiency. Trace amounts of water can play a profound role in improving the reproducibility, resolution, and efficiency in the normal phase HPLC. Thank you so much.